who will talk about fire tests and mass timber. And we're grateful to have Stephen here, all the way from Ottawa. He's from CHM Fire Consultants, and is the founding partner of CHM Fire Consultants, and serves also as an adjunct professor in the Fire Safety Engineering program at the Carleton University. He also was a research scientist with Canada's National Forest Products Research Institute, previously to that. Dr. Kraft has also been involved in over 20 significant mass timber building projects across Canada. Welcome, Dr. Kraft, to the stage.
Great, thank you. Thank you very much, and thank you to George Brown College, Brookfield, and Rotherglass for the invitation to speak today regarding the mass timber demonstration fire test that we conducted last year in Ottawa. It was a 3-year project. It was a pretty big undertaking on the order of $3 million project to plan, construct, and conduct a series of 5 fire tests. Just a little bit of background on CHM Fire Consultants. We've been working with mass timber pretty much since it was founded in 2011. We had some early projects like the Wood Innovation Design Center in Prince George for UNBC, the Liverlost Place next door. We completed the alternative solution to allow for mass timber for that project, as well as University of Toronto's Academic Tower. I think Trinity's, the 6-story Trinity project was mentioned by Lee, among others. So there's quite a few, both under construction now, but also nearing the end of design in Ontario, which is great to see. Before I jump into the mass timber demonstration fire tests that we conducted last summer, I'd like to give just a very brief background of kind of where we are with fire research and mass timber. We've come a long way since the very first test that I conducted back in 2009. These were the first fire resistance tests on CLT that were conducted in North America. At the time, they were what we call intermediate scale tests, so just 4 foot by 4 foot CLT panels. There was no press at the time, so they were constructed just in a laboratory. And I'll just touch on just one or two attributes of each series of tests. And the message I'm getting across or that I'd like to get across, is that we've learned something on every set of tests we do. And so that's a really important thing to keep in mind, that we don't have all the answers today, and so research is continuing to develop our understanding of mass timber and how it performs in fire. These very first tests were really interesting. When we look at these were tests on 3-ply cross-laminated timber, and we had expectations on how long it would take basically to char through the panel, and so overall fire resistance for the CLT panels. And there's different types of adhesives that were used, and in these tests we had one adhesive that's known to have great fire performance. It's been used in glulam for decades, and we know it performs well. And there was another newer adhesive that we had some questions about. But in these very first tests, it was actually the adhesive that performs really well in fire that in these tests allowed for the fire to basically burn through the panel in under an hour, which is quite surprising given that we were expecting something on the order of 2 hours. And in fact, the picture on the right is at 2 hours and 5 minutes into a fire resistance test, and it's still cool to the touch. So it turns out that just with the 3-ply panel, if the adhesive doesn't do a good job of sealing up the CLT panel, then you can get basically burned through, kind of starting at a pinhole and growing. So we learned something there. That was instructive. A couple of years later, we did the very first full-scale fire resistance tests on a CLT floor assembly at the National Research Council in Ottawa. And this was interesting. This was the first case where we saw this phenomenon that we've developed and understand much better now. But the idea being that the mass timber itself requires a significant amount of heat to burn. And without that heat, basically the fire goes out. And these tests were a great example, whereas at the end of the test, where the gypsum board has fallen off this particular floor assembly, the floor assembly was lifted off the furnace, and as it starts to move away from the furnace, the flaming basically went out on the CLT. As soon as it moved away from this furnace that's on the order of 1,000 degrees Celsius, as soon as it got away from that heat source, the flaming largely went out. And so that led to, in the next year or two, some compartment fire tests at Carleton University, where we wanted to better understand how the mass timber affects the fire dynamics in a compartment. So basically the question being, how much wood can we expose in a compartment and still see the fire burn out when the room contents are consumed? So for example, the furniture in a room, when it's consumed, does the fire burn out or does it continue to burn? In this set of tests, these were the first set of tests that we learned that we had this issue or this phenomenon of CLT layers falling off, and which could lead to fire regrowth because we were losing that insulation layer of char that helps the panels, helps the fire die down. So that was instructive. National Research Council, subsequent to that, conducted some tests, particularly the ones in 2017, which were geared towards basically development of the building code to allow for tall mass timber buildings. And they were able to reproduce the same phenomenon of char layer falling off of CLT, allowing for the fire to regrow to fully developed fire again. So based on that, there were some tests done to look at adhesive performance in CLT. In 2018, the product standard for CLT was modified to include a full-scale fire test to look at this phenomenon, the fall off of char layer of CLT. And so that change was made, and with the qualification of new adhesives to meet that criteria, then we had this, quote, second generation CLT. Then we wanted to understand how that performed in compartment fire tests. So NRC in 2018 was able to run some tests with this second generation CLT, and as expected, it performed much better. And so having completed those tests, there were some other tests that occurred in the US as well as around the world that gave us some confidence in terms of understanding how the fire performs in a CLT compartment, perhaps how many walls can be exposed versus ceiling. So we had some idea of that, but there's still lots of questions that we had. Does that extrapolate up to an open office floor plan where we have many tall mass timber buildings being built that are much larger floor plates, much larger fire compartments? How do they perform? And as well as better understanding some of the benchmarks. So the way an alternative solution works in the Canadian building code and the provincial building codes is basically you have to demonstrate that the proposed design is as safe as what the code requires. So up until 2020, that meant comparing to non-combustible construction. And basically what that meant was when the fuel contents are consumed, the idea is that we want to see that the fire dies down on its own. It's not going to continue to burn. Because if it continues to burn, then it's going to challenge the fire resistance rating of the structure, fire resistance, and potentially we could see a high-rise building collapse, which is obviously not something that we want to see. So the idea is we want to see that the fire is able to burn out on its own. And so some of the testing that was previously done, it always compares back to a baseline of basically the same CLT compartment lined with 2, perhaps 3 layers of gypsum board. So it's basically a completely non-combustible compartment. And that's always the baseline from a research perspective, which was great because we really wanted to know the contribution of mass timber. But when it comes to the code, and comparing to non-combustible construction, there's lots of combustibles in a non-combustible building. We can have combustible wall finishes, we can have combustible ceiling finishes in a non-combustible building. And so from an alternative solution design perspective, we were interested in creating a baseline of what the acceptable code provisions were. And then the other priority for these tests was looking at construction site fires. We've heard a little bit of discussion earlier on insurance costs for mass timber during construction. In addition to insurance, there's some rather challenging requirements in the fire code for mass timber buildings under construction. There are requirements to encapsulate as the building goes up, leaving no more than 4 stories unprotected, as well as a number of other requirements. And those tend to be quite challenging because often the building's not weather tight. And so the idea of putting up gypsum board or perhaps gypsum sheathing applied to the mass timber as the building's going up. And if it's getting wet, then that's problematic. So we wanted to look at construction site fire safety and what fire growth in a building under construction might look like. I mentioned this was a very large undertaking on the order of about $3 million. We had funding from Natural Resources Canada, Ontario, Quebec, Alberta, BC, as well as the National Research Council contributed significant funding and support. And then we have a long list of partners here, those that contributed to the design, the supplying mass timber. We had mass timber supplied from 5 manufacturers from across Canada, and we had sponsors providing material for the test structure. Just a little bit on the structure. The next few slides give an overview of the structure. It's pretty large. As far as testing goes, previously most tests were on the order of perhaps the biggest ones were a 2-bedroom kind of apartment size. We wanted to look at an open office floor plan. So the first story of this structure was a total of 4 bays, so 3 across the front and then 1 behind on the right. And they were 7.2 meters span, so pretty large span. And on the order of 4 or 4.2 meters floor to ceiling height. So that was really representative of commercial construction, and that's what we were after with that first story. And then the second story was more perhaps typical of residential construction. So the idea was that this structure was representing a tall mass timber building, so it was designed to represent the 4th and 5th story of a 12-story mass timber building. So in terms of the size of the members, they were sized to take the loads that we would expect in a high-rise building. At about the 4th and 5th level, as well as the mass timber was designed for 2 hours of fire resistance, so beams, columns, CLT floors, so floors were 7-ply, CLT to make that large span, and of course connections designed for 2 hours. As I mentioned, we had supplied CLT from 5 manufacturers across Canada, which made for some fun design challenges, integrating that together. Just a little bit about the exterior walls. They were steel stud with basically 1 hour fire rated walls. So 5/8 type X gypsum on the interior, rock wool insulation in cavity, gypsum sheathing on the exterior, and then 3 inches of rock wool comfort board on the exterior. And that was just designed to be typical of what we're seeing on many projects. So as I mentioned, we had some different objectives we were after. We did a total of 5 tests. The first one being the fully furnished office space, so that was the entire first story of the structure. We had 2 residential units side by side, which we'll look at. One was what we call, it's listed here as protected, but basically it complied with the requirements for non-combustible construction in the code, and comparing that to exposed mass timber. And then we had 2 construction site fire scenarios, one with a smaller garbage can fire, and then one with a much larger fuel load. Here are some floor plans of the structure. And in addition to those 4 bays, we also had an exit stair framed in behind one of the 2-story CLT wall. We wanted to demonstrate how cross-laminated timber can perform as a fire separation to an exit stair. And then you can see on the 2nd story how we split up the 2 residential suites. They were on the smaller side, of course. And then we had what you see is residential suite C, the corner bay on the 2nd story. That's where the large construction site fire occurred. The smaller one was in what's listed as residential suite B. We reused that compartment after it was used for the residential fire test. So here's just the 5 tests listed out. Again, I'll go through each of these as we look at the actual pictures, perhaps. So here's a comparison of the 2 residential suites side by side. The one on the right was the non-combustible construction compliant room. We had 1 inch of basically plywood, 2 layers of 1/2-inch plywood on the walls, and we had fire retardant treated plywood on the ceiling. So that complied with the flame spread requirements for non-combustible construction. And we compared that to the room on the left, where we had 2 columns exposed, mass timber columns, glulam columns. We had a glulam beam, and then the ceiling was fully exposed. And both of these rooms were identical in terms of furniture and whatnot. You can see the room on the right is the baseline scenario, so the code-compliant solution for non-combustible construction, and the one on the left is the mass timber suite. So here's some pictures during the test. This kind of helps us compare. So again, the pictures on the right side are the non-combustible acceptable solution, the one on the left being mass timber. And you can see from a fire development perspective, they're very similar. We saw slightly faster fire development in the non-combustible construction compliant room. Not surprising, we had more mass timber or more exposed wood surface in that room. And then we see from a decay perspective, so at about almost 5 minutes, we saw basically full room involvement. And then as we're getting close to 30 minutes, we're basically seeing the fire die down. Both rooms, and again, a little bit slower in the code acceptable solution for non-combustible construction. So this is helpful. This is, perhaps this is a bit of an extreme case. There's not many residential suites you see in a non-combustible building with plywood on the walls and fire retardant treated plywood on the ceiling. But it is a code acceptable solution. So it does give us one more data point to look at when we're looking at comparing how mass timber performs. So if we look at temperatures in the room, I won't get into too much detail, but if we just look at the mass timber suite compared to the baseline suite, there's not a significant difference between basically the fire exposure in the 2 rooms, and perhaps the baseline suite with the plywood on the walls was a little bit worse. So that was helpful. Next is the 2 construction site fire tests that we did. The first one being a garbage can fire. One of the ideas behind this test is to look at or to demonstrate how difficult it is to get mass timber ignited and burning. It's not. It's much more difficult than what we typically know from light frame construction. For example, with a propane torch or a propane heater, it's going to be quite difficult to get the mass timber ignited. This was a really interesting test. So NRC had developed a standard garbage can fire scenario where we basically designed a garbage can to be as severe as possible for a fire, for a garbage can fire. So you see that there's ventilation strips cut in the garbage can to provide air, and a wood crib placed inside to fill it. So pretty much optimized to give the most severe fire exposure possible from a garbage can fire. So this is really interesting. As you're looking at these pictures, keep a close eye on the time. You'll notice the first, or from 0 to the top picture on the left to the top picture on the right is 0 to 20 minutes. So it took 20 minutes, nothing really happened. So the garbage can fire was burning. The garbage can was up against the back wall, which was exposed CLT, as well as the ceiling is exposed CLT. You can see some discoloration just because this room was used. This was the second fire test being conducted in this room. And then it was really interesting at about 21 minutes, the back wall ignited, and very quickly from 21 minutes to essentially 23 minutes or so, we got a fully developed fire. So basically the wall ignited, the ceiling ignited, the fire spread, and it became a fully involved room fire. But just as quick as it grew, by the time we got to about, say, 24 minutes, the fire went out on the CLT. So within just a minute and a half, basically, the CLT charred over, and then the fire was no longer strong enough. It wasn't putting in enough heat to keep that mass timber burning, that CLT wall and ceiling burning at a fully developed phase. And so we see that by 24 minutes, it pretty much dies back to just the garbage can. And then all of these tests, we basically let go for 4 hours to see what would happen. And so nothing, as the garbage can fire died down, at 35, 40 minutes, nothing happened after. You'll notice just the temperature on the left, top left is the middle thermocouple tree. And so you see a very quick spike of just a minute or two of high temperatures. And then it basically died down on its own. The next test, again, a construction site fire scenario. So when we look at construction site fire scenario, we're looking at basically fully exposed mass timber. So we've got the CLT floor exposed, glulam beams and columns, and CLT ceiling exposed. And in this test, we actually had light frame wood walls framed up. Another challenge within the fire code, the National Fire Code for tall mass timber buildings, or encapsulated mass timber buildings, is that the light frame wood walls that are placed in the structure also need to be encapsulated as the building goes up, which basically makes it not feasible to do at all, because by the time you're 4 stories just below from the top story as the building's going up, you're nowhere close to ready to put services in those walls. And so it makes, if you have to clad those walls in gypsum board, then it makes it not practical. So we wanted to look at that. So we included light frame walls, and we had 6 wood cribs, which makes for a pretty large fuel load. So this is what the interior of the space looks like. So it was the entire bay on the top story in the corner. And looking here, we have our fire development. It took about 8 minutes. So all these fires were basically started, well, I should say this fire, as well as the next big fire we'll look at, were started with wood cribs and basically a pan of heptane fuel below the wood cribs. So basically designed to create a fast-growing fire. So in this case, it took about 8 minutes for that fire to grow up through the wood crib and then spread to the wall and ceiling to become fully involved. And you'll see from 8 minutes to 18 minutes, basically we've gone through the fully developed phase and the fire is starting to die down. And at 25 minutes, the fire is most of the flaming is largely gone out. And you can see on that top row of pictures, the top 2 rows of pictures there at the same time. At 25 minutes, looking inside the compartment, we have some flaming of those wood cribs that were on the floor. The interior wood partitions have pretty much all fallen down, and so we just have some coals on the floor. In this particular test, we let it go for about 2.5 hours. We had to stop this one because we were still getting smoldering combustion. It was a windy day, And so there was, even though there's no flaming combustion, it was still smoldering, generating quite a bit of smoke, and the smoke was blowing towards some buildings on the campus. And so it had to be ended at 2.5 hours. And then lastly, this is this was the big test, intended to be test number 5. But because of construction delays and building construction, we ended up having to do this test first because it was in conjunction with a 2-day seminar that the Canadian Wood Council had organized. So this was the first test we did. This is, as I mentioned, a large space with, with fully furnished office, but with mock furniture. Because of restrictions on the site, we couldn't burn plastics for the smoke that it generated, so we were limited to burning wood products. So we had to reproduce the office fuel load with basically wood cribs and wood desks and whatnot. So in this case, we have an exposed CLT ceiling, exposed beams and columns, and then we had basically cement board over the floor, 2 layers, to basically mimic concrete topping, which is pretty much typical for tall mass timber buildings. So this is just a plans view of this. So it was the entire first story, and we were monitoring the exit stair shaft for fire and smoke. Now, one of the motivators of doing this whole test program was to demonstrate the fire performance of mass timber, and all that research that I covered earlier, that I skipped over quickly. That's all taking place in a lab. So you might have 1 or 2 people come witness the test, but basically it's not open to the general public. The idea here was that we were inviting building officials and fire service, insurance companies to this test to witness the fire test, as well as some other industry practitioners. So the idea was to be able to get them to site, witness a fire test, because most people never have the opportunity to witness a fire test, and it certainly gives you an appreciation for what a building is exposed to when there is a fire, as well as we've had challenges submitting alternative solutions for tall mass timber buildings, where it's really hard to get perhaps the building official or perhaps it's the fire service to read a 100-page report on why the building's safe. And so the idea was if we could get them to witness the fire test, then hopefully that would go a long way to helping them understand the past research that's been done, but also appreciate what goes into a fire test. So we had, over the course of the 5 tests, we also had another test where we had I think 30 fire chiefs from across Quebec come witness one of the construction fire tests. So overall, I think we had 200 people come witness these tests, but we had about 150 at this particular test. I think there's perhaps a couple people in this room who were able to witness this test. I think it was, to say the least, it was quite impressive in terms of the severity of the fire. Those people that we had seated under the tents to witness the fire test, we cleared that out within, I'd say, about 6 or 7 minutes into the test, because the heat from the building, even though they were perhaps 100 feet away, was so intense that everyone stepped back. You can see at about just over 5 minutes, we basically get ignition of the ceiling, and then that spread across the ceiling between the bays. And by about 7 minutes, we had full fire compartment involvement, so all 4 bays. And it burned quite vigorously. You can see at 15 minutes it's still burning quite vigorously, but by 25 minutes, essentially the fire had died down. The furnishings had been consumed to the point where the flaming on the CLT ceiling and the glulam columns and beams went out on its own. So the flaming combustion completely went out on the structure at about 25 minutes roughly. And you can see at 60 minutes there's nothing, and basically it went for 4 hours and nothing further happened. So at 55 minutes, here's a couple pictures. There's still a little bit of burning debris on the floor, but you can see the structure itself, while charred, is in good shape. To give you an idea, so this was a very intense fire. Even though it was relatively short, it was very intense with the large window openings. 3 inches into the CLT ceiling panels, so the 7-ply CLT panels that made up the ceiling, 3 inches in, there was basically a 1 or 2 degree Celsius temperature rise at that point. The char depth was on the order of about 1 layer of the 7-ply CLT, so about 1.5 inches. But 3 inches in, there was virtually no significant temperature rise. Keep in mind, this is in the, I would say, extremely rare scenario where for whatever reason, the sprinkler system has failed to control the fire, because all these tall mass timber buildings are all sprinklered. And it's in the even rarer scenario where the fire service, for some reason, can't get to the fire and put it out. So for whatever reason, perhaps it's in a seismic zone as post-earthquake, there's no water. So the idea being that we want to see that the fire is going to burn out in that extremely rare scenario where there's no intervention from the fire service and the sprinklers, for whatever reason, haven't been able to control the fire. So I'll mention here, I think there was over 1,000 channels of data collected during these tests. So temperature, heat flux, and NRC, National Research Council, who ran these fire tests, collected all that data, and they've published it all in a report, which I'll show a link to at the end. Just showing temperatures during tests. So there's lots of data that's available for analysis. So essentially, in all of the tests, all 5 tests, in all 5 tests, we saw fully developed fires. I say should be 4 of the actual mass timber tests. In all 4 tests, the fire died down on its own, and once the fuel, the furniture was consumed, or in the case of the construction site fire, the garbage can. So these are NRC's findings. I'll just summarize them on the research. Basically, all scenarios, basically we saw the mass timber burn out on its own without intervention. Post-test firefighting operations required to fully cool down the remaining deep-sea fires. So basically what we saw, particularly in that the construction site fire on the 2nd story corner unit with the wind blowing strong that day, was we saw continued smoldering. So the fire service at some point does need to show up and extinguish the smoldering. The char depths that we measured in all of the tests were all less than what the structure is designed for in terms of a 2-hour fire resistance rating. The conditions in the stairwell, which were separated from the 1st story large open office fire test, the exit stair shaft on the other side was unaffected. And basically the structure remained stable even after 5 fire tests. We were monitoring char depths and strength of the structure from test to test to make sure that it wasn't compromised. A large part of the structure, when it was torn down, the panels and the glulam beams and columns went to, I think, perhaps 3 or 4 different universities, as well as FK Innovations, for various projects. Some on blast testing. Some panels were largely unscathed, and so they could be used for other research. And then some of the panels are being used for looking at research on rehabilitation of the structure post-fire. So with that, if anybody's interested in the NRC, the National Research Council's report on these tests, it's available at the following links, or you can contact me. I'd be happy to share it. And I'd be happy to take any questions.
We have time for a question from the audience, if anyone wants to ask anything of Dr. Kraft. Any questions? No, exactly. Well, thank you, Dr. Kraft. Appreciate you being here, and I'm sure if anyone has questions, you'll be here for the rest of the afternoon still, and if we join us for the dinner afterwards, we'd love you to be our guest.